Measure Tom Smith.
Thanks very much, Doc. It's a pleasure to be here, and thank you for the opportunity. Okay, I think we'll just get right in. I'm going to do it in two parts. So one is just a little refresher about econometrics. So let me start with that. Okay, so let me start with that. So there's four different methods that you can do your econometric analysis, right? And we'll go through these. The first is maximum likelihood, and I think you're very familiar with that, right? Second is Bayesian. And third is GMM, which stands for Generalized Method of Moments. And the fourth is Bootstrap. And I'm sure you've heard of all these, but we'll just do, just so we're on the same page, we'll just do a brief overview of all of these. So firstly, the maximum likelihood approach is you make assumptions about how your data is distributed, right? So normally in maximum likelihood, people make the assumption that the data is normally distributed, yeah? So normal, zero, sigma squared I. It's a very strange assumption to make, right? When you think about it, right? I know, you know, the use of maximum likelihood is pervasive, but it's a very strange assumption to make, because just about, you know, nothing that we look at is normally distributed, right? So, for example, we know that returns are definitely not normally distributed. In fact, if there was a distribution, it would be like a log norm, right? Because share prices can't go below zero, and they're very highly skewed to the right. So even though, you know, we've studied this a lot and thought a lot, it's really quite a strange assumption to make, because we really don't know what the distribution of the data is. And that's why some of the other methods like GMM and Bootstrap have a distinct advantage. So here we're going to go through the regression case. So we'll mainly do the regression case. So if you assume that your error terms of the data is normally distributed, what you're saying is the probability of Y, given the parameters, you know, which is beta and sigma squared, and given the explanatory variable X, are distributed normally. Yeah? And that's what the normal distribution looks like. The way we deal with that is we take the natural logarithm, yeah, which gives us this. And then we want to maximize that likelihood with respect to the parameter beta. And that's how we end up with the beta equals the covariance of X and Y over the variance of X. Yeah. So that's all of the results that fall under the linear general model, right? And you would have done this in your first level statistics and any econometrics course you did. The second approach is Bayesian estimation. And again, you make assumptions on the data, yeah, probably Y given theta. But here the assumptions are, you know, given theta, given the parameters, and you also have a prior about what theta, that is your parameters, would be. Am I going too fast? So it gives you, the advantage of Bayesian is it actually does give you the distribution of the parameter of interest, that is theta, the underlying parameter. The maximum likelihood approach strangely gives you the distribution of the sample estimate of the parameters, you know, theta bar. So the other advantage of Bayesian is it puts the problem in a decision-making context. That is, you have a prior. Yeah, okay, I think this is the way the world looks. You have this prior, you look at the data, and then you update your priors given the data to form a posterior. So this is the posterior. The probability of your parameters given the data equals what you initially thought the data would look like, you know, given your priors. Yeah, and so it does enable you to distinguish between competing models. Yeah, given the priors and the data, even when they're non-nested. So that's quite a, you know, quite a good thing. Right? You can look at the Bayesian odds ratio. So in the regression case, you'd make the same assumption about the data, the probability of Y given the parameters beta and sigma squared and the independent variable x, has this normal distribution. And then your priors can be either uninformative, that is, they're proportional to the variance, or what they call conjugate. And what that means, conjugate means that it goes with the distribution you made on the data. So something that goes with a normal distribution is a normal, because they're both e to the minus or the inverted gamma. In either case, the distribution of beta given y reduces to the familiar t-distribution from ordinary least squares, from maximum likelihood. For the Bayesian estimation, you saw that regression case, you get almost identical. Outside of the regression case, though, it's sometimes hard to get analytical results. Yeah. And that's what initially stopped the progress of Bayesian estimation. But now with the advent of modern computers, numerical methods are used, and something known as MCMC, which stands for Monte Carlo Markov chain. Yeah, Monte Carlo Markov chain. Yeah. And in doing this, to do the Markov chain, there's the Monte Carlo, there's a Gibbs sampler and a Metropolis Hastings sampler. So the Gibbs sampler says, in order to get the probability, the joint distribution of x, y, you first draw from x given y, and then use that value of x to draw from y given x. And you keep repeating that many times. And under regularity conditions, the result of that, which is quite easy to do, will converge to the joint probability of x and y. And Metropolis Hastings is a more general case. The Gibbs samples actually turns out to be a special case of Metropolis Hastings, right, when the distribution is reachable from. So with the Metropolis Hastings, you approximate the target distribution by something that's easy to use, and then you make an adjustment. Yeah? And the Gibbs sampler is a special case of the Metropolis Hastings, because they're the two samplers that are used. You'll find lots and lots of examples in the article by Johannes and Paulson, Monte Carlo Markov chain method for financial econometrics. The third method that's used is GMM, and a generalized method of moments. And it makes no distributional assumptions whatsoever. It just relies on the central limit theorem. That is, in a large sample, the means of what you're estimating will be normally distributed, and that always works. In the regression case, you simply set up moment conditions for the first order condition of ordinary least squares. So when you differentiate the likelihood, right, or when you differentiate y minus x beta squared, you get this for the alpha, y minus x beta, and you get this for the beta, the error term times x. So this is the expected value of the error term equals 0, and the expected covariance between the error term and the x variable is 0. So they're called the normal equations of OLS. One that defines the alpha, first order condition defines the alpha, first order condition that defines the beta. You will get, if you estimate this, identical parameters to the maximum likelihood, to ordinary least squares. However, if the assumptions of maximum likelihood are satisfied, you get the same standard errors, right? But if the assumptions of maximum likelihood are not satisfied, you will get the correct standard errors. So what you've done here is you set up the GMM in such a way that you nest the maximum likelihood estimated, right? And if the assumptions underlying maximum likelihood are true, then you will get exact same standard errors and exact same inference. However, if the assumptions underlying maximum likelihood are not met, you will actually get a far more correct standard errors. So that's an important distinction. And the generalized method of moments has really taken off, right? Just about everyone does this distribution estimation, right? And in fact, every time that you do a regression and choose robust standard errors, you're actually doing GMM, right? You're estimating or less coefficients, but you're doing it with the GMM standard errors. So every time you tick the box that you want robust standard errors or heteroscedastic autocorrelation consistent standard errors, then you are doing GMM. The final method is the Bootstrap. Yeah, and here, the same as GMM, you say, well, look, I really don't know what the distribution of the population is, right? But I do have the sample, and I'm going to take the sample as representative of the population. So, for example, right, my world, I'd be looking at market returns and say returns from 10 different, decile portfolios, 10-side portfolios. So I might have 1,000 months of data on each of those 11 returns. So say I wanted to calculate a test statistic for a test, I'd generate a random sample from the database. And so what I'm going to do, since I've got 1,000 months, I'll just choose a random number between 1 and 1,000. And I'll say, well, I'm just going to pick out that row of this 1,000 by 11 data matrix. So then I draw another random number and pick out that, the corresponding row. In fact, maybe if I wanted 1,000 observations, I'd draw 1,000 random numbers, with replacement, and I'd add that row. So then I have a Bootstrap sample of 1,000 observations that I drew from the actual sample data. Then I calculate the test statistic, and it might be whether the alpha is equal to 0. And then I record that test for use later. So then I repeat step 1, say 10,000 times, and record the test from each of these repetitions. So then, once I've done the 10,000 different tests, I would sort the test from lowest to highest. And if I take the 250th value and I take the 9,750 value, that gives me the lower 2.5% and the upper 2.5%. And it gives me the 95% confidence interval. So it's incredibly easy to use. It's only like 1 or 2 lines in an R program. So it's based on the work of Brad Efron from Stanford University. It is incredibly simple to use, makes a distributional assumption. It is widely applicable, and interestingly, I'll just highlight this, it's the basis for big data and machine learning, right? So incredibly useful technique to have. So going back, I think you knew these things, but maybe didn't put them together. 4 different estimation approaches. Maximum likelihood, which is mainly you do ordinary least squares. Bayesian, where you have a prior, you look at the data and you update the prior. Generalized method of moments, well, you can nest the maximum likelihood, you get the same estimates, you'll get the same standard errors if the assumptions underlying maximum likelihood are met, that you'll get the right standard errors and the right inference if the assumptions underlying maximum likelihood are not met. And the Bootstrap, incredibly easy to use. You treat the sample as representative of the population, you draw from replacement. From that sample, you do a whole lot of tests, and then you're able to get the confidence interval of your parameters. And it is the basis of big data and machine learning. So these 2 methods are used more and more, right? They've come to sort of take over the econometrics world. Just checking the chat. Yep, it's all good. So that's yep. So let me make sure that the interpreters are catching up.